Good morning, everybody. This is a live severe weather briefing with a lot to talk about today, but mainly we're going to be focusing on a few days ago, the insane tornado that happened in southwestern Manitoba. I want to do a breakdown of the storm structure because this was such a perfect storm, almost like the skeleton of a supercell, almost like a supercell, tornadic supercell diagram. I want to break down some of the basics of storm structure and the clear slot, the rear flank downdraft of a tornadic supercell. This is the perfect storm to break it down. Here is Sean Schofer's video. This is from the Dominator 3. He was by himself actually on this day, so quite a career intercept for Sean to be around this tornado from extreme close range like this. Initially, he was looking off to the south of this tornado. This direction right here, he's looking off to the east. And you can definitely see that well-defined clear slot wrapping around the tornado. This was his initial view, looking off to the south, shot vertically to capture that funnel. You can see the condensation funnel in the middle. That's cloud matter. You can see the debris on the bottom. This shows some of those mesovortices or subvortices that were rotating around the base of that tornado. Many of those mesovortices were condensed as it was going through that field. And below such a high cloud base, whenever you have condensation reaching the ground, that means there are extreme pressure falls within that subvortex, and the pressure gradients around that ramping up so quickly. The wind speeds are likely difficult to fathom within those subvortices as that tornado vortex interacts with the friction of the earth, causing extreme damage. Sadly, here at this farmhouse, there were 2 fatalities caused by this tornado, and it threw vehicles, lofted vehicles, up to 200 yards away from the vortex. Storm chasers like Sean Schofer, Aaron J. Jack, were first on the scene there doing search and rescue as well. And very sadly, as I mentioned, there was loss of life caused by this tornado. And this just shows that tornadoes, even though they're beautiful like this, they're often associated with a dark side, and that is the damage and loss of life and property that they can leave behind. And in this case, this is a very powerful tornado as well. And here is a still photo, also from Sean, looking at this storm structure. This is looking off to the east, as I mentioned. And I'm going to break down this storm structure here, and then we're going to break down the environment that led to this tornado and why this tornado happened meteorologically. We're also going to be plotting some hodographs. We're going to try to see what we can infer from the wind speeds at different layers of the atmosphere. We'll plot out that hodograph and see just what came together to produce a tornado that looks like this. You can see this massive tornado vortex in the middle. This is a condensation funnel right here as well. You can see the condensation funnel in the middle. That's cloud matter. This right here is the debris cloud back below it. Lofting that debris pretty far out, even though the debris desires to stay close to the tornado with that pressure gradient. Some of the mass of the individual debris is such that it will get flung out a little bit further than that condensation funnel. And the one thing that really stands out here, and this is a west to east oriented road, but is the clear slot. This right here is an area of descending, drier air that encapsulates the vortex within. So if you can imagine a cylinder of sinking air encapsulating a sheath of inflow air that is more moist and rising also, usually rising within the middle of it. And then on the outside, you have this sheath of sinking air. That is a subset of the rear flank downdraft. It's basically on the north side of a bulging rear flank downdraft. You can even think of the RFD almost like a dry line of a synoptic scale storm system, where on the north side of that dry line, it often bulges in to a surface low. And on the smaller scale, on the tornado and the storm scale here, or the small mesoscale, this sinking air or drier air that's on the north side of the RFD can actually wrap into the mesocyclone. We call that a clear slot. And when the pressure within the low-level mesocyclone reaches a certain point, it causes the wind around it to be thrown out of balance. And that sinking air that's on the backside of the mesocyclone can cut across isobars and cut into the middle of that low pressure. The atmosphere is always trying to achieve equilibrium and alleviate those pressure discrepancies, whether that anomaly be a high or a low pressure. So in this case, the wind is trying to flow in toward that low pressure, and when the low-level mesocyclone intensifies as such, The descending air on the backside of the mesocyclone cuts across isobars into that lower pressure, and that manifests itself as the clear slot. So usually you'll see it happen right as a tornado is about to form, or as the storm is just starting to go through its motions. You'll see clear air begin to cut into the mesocyclone like a bit of a slot, and then you'll see a lowering or a wall cloud on the north side of that clear slot begin to rotate. Sometimes they happen at the same time. Sometimes the funnel will form and then the clear slot will wrap around it. And there is quite a bit of debate as to what comes first, the clear slot or the tornado, almost like the chicken or the egg type of a debate. In my opinion, the clear slot comes first, accelerates cyclonic vorticity on its northern side, and it's already underneath the vacuum cleaner of a mesocyclone, getting stretched above it at all times. So anytime you get an eddy on the north side of that clear slot, or even a gustnado associated with that surge in clear slot, once it gets coupled with the extreme updraft within the mesocyclone, it can turn into a tornado like this, fully coupled with the mesocyclone, a clear slot wrapping around it. The original mesocyclone was likely a big saucer that didn't have a tornado but a massive base, and then once it started to gain strength, that low-level pressure started to drop out. That's when it had a clear slot, and then began what we call the process of occlusion. And once occlusion happens, this dry sinking air at the north side of the RFD bulge wraps all the way around the inflow air and enclosing it within. That's a cyclonically rotating vortex of relatively moist air from the original updraft to the mesocyclone that gets enclosed in there. Continues once it gets coupled with the mesocyclone above, the pressure continues to fall. It undergoes a series of positive feedbacks and becomes this massive tornado cyclone here. And this is looking off to the east. As I mentioned, this is the clear slot. And sometimes these occlusions can be so robust that they can actually kill the storm. So one thing that you'll hear us mention when we're storm chasing out there is, man, does this mesocyclone have a skinny occlusion? That's a negative factor for tornadogenesis, because if the wind shear is not quite right, maybe the instability's off, maybe the pressure fall within that mesocyclone is not quite dramatic enough, so then the cross isobaric flow is not quite as dramatic, and you just get a small clear slot on the back side of this mesocyclone, just a little sliver, and oftentimes that there's not enough mass on the cyclonic side of that clear slot for it to become a fully coupled tornado with the mesocyclone. But when you see those clear slots punching right into the middle of the mesocyclone, that cross isobaric flow, there's a lot of mass, a lot of inflow mass on the cyclonic side of that clear slot. That's when you know that that storm is a candidate to become a prolific tornado producer, and you know that the shear, especially the wind shear, is likely favorable for that storm to produce tornadoes. But this is just a perfect still photograph of a tornado to really get an idea of what's going on dynamically and meteorologically inside. And again, this photo was taken in southwest Manitoba just a couple of days ago. Sean Schofer shot this thing. And when we're looking directly up at a cinnamon bun, that's a funnel that's coupled with the mesocyclone, but often is not quite reaching the ground yet. And we're looking aloft at a cinnamon bun funnel like we saw in the Nebraska Panhandle, where you could see the clear slot wrapping all the way around. That cinnamon bun funnel has accomplished occlusion, which means that the north side of that RFD, or the clear slot, is wrapping all the way around that vortex. And even though it's not touching the ground, it is a cinnamon bun funnel and could develop into a tornado that touches the ground. And that's why you're always scanning the ground for those little dust whirls or gustnados that are associated with the clear slot that could get fully coupled within that mesocyclone. And you'll often hear many storm chasers say, you know, where's the mesocyclone here? This storm has no updraft. But really what you're looking at is a scale that's much smaller than the mesocyclone. The updraft, rotating updraft above, that's termed the mesocyclone, is on the order of 5 to 10 kilometers in scale. And this right here is actually the tornado cyclone, with the mesocyclone extending much longer beyond the scale of this still image. Basically, like if you can imagine a big flying saucer above it. What you're looking at, though, is just the apex of that clear slot that is wrapped all the way around the tornado vortex within the mesocyclone. And this occlusion was so substantial relative to the size of that mesocyclone that it actually acted to weaken the storm Basically, it took out all the mass of the mesocyclone. You can still see some updraft off to the northeast of this thing from some photographs that are a little bit further away with this little tornado on the backside. But this is just the occlusion within the mesocyclone here. You're looking at the tornado cyclone with a textbook clear slot rotating around it. And I might be able to explain this a little bit better on just a blank piece of paper here. Pretend that we are looking straight down on that mesocyclone. So imagine a mesocyclone that is almost perfectly circular. It is kind of hard to draw using the finger here. But there's the low-level mesocyclone on the order of about 10 kilometers across. So pretend that this is 10 kilometers across, realizing that tornadoes are on the order of about a kilometer across. So the scale of a tornado cyclone is probably about a tenth of the scale of the mesocyclone. And as the low-level mesocyclone intensifies, the low pressure in the middle also intensifies, and that's driving wind around it in a counterclockwise manner in the northern hemisphere. And also there are concentric isobars within this of equal pressure, and those isobars tighten up around that low pressure. So when I say cross isobaric flow, that's wind that's going across these isobars in toward the low pressure. But initially, as this mesocyclone is slowly intensifying, the wind around it is in what we call cyclostrophic balance. So it's rotating around in a counterclockwise direction, and it's balanced by centrifugal force directed outward and pressure gradient force directed inward toward that low pressure. And when these two forces oppose each other equally, then the flow is in cyclostrophic balance here, rotating around. There is a little bit of deflection due to the Earth's rotation out here as well. And we're in the mesoscale, when you're talking about a mesocyclone, you do have to factor this in just a little bit. But the centrifugal force is much greater, matters a lot more on the synoptic scale, or that on the order of 1,000 kilometers, talking about low pressure systems or big mid-latitude cyclones. But when this flow is in balance, cyclostrophic balance, and you're basically neglecting Coriolis force on a smaller scale like this, and this is cyclostrophic balance. But when the mesocyclone intensifies, then this pressure gradient force becomes much greater than the centrifugal force that's directed outward. And so oftentimes with these mesocyclones, imagine that you're looking down toward the ground at a mothership supercell. Usually you get a dry downdraft on the backside of this, on the up shear side. And this is the beginning of the rear flank downdraft. So it descends on the backside, and because of this rotation, a lot of times that drier air will surge on the south side of that low pressure that is the mesocyclone. That's the RFD gust front that we talk about. You get strong westerlies a lot of times on the south side of that mesocyclone that ramp up as you get closer to the south side of that tornado. That's why you often get RFD damage as well from close range on the south side of the tornadoes. This is why I usually try to do a hook slice maneuver on the north side of the mesocyclone. You stay out of those very violent RFD winds that are a lot of times concealed in dust, and you do get a lot of big hail up here when you're trying to do a hook slice maneuver to gain visual of that developing tornado off to your south. But this is the area of sinking air right here that is the beginning of the downdraft, wraps around the south side of the mesocyclone. But when the mesocyclone intensifies strongly enough, and that low pressure ramps up too fast for the wind to maintain its cyclostrophic balance, and also aided by the additional momentum of the sinking air on the backside. It's already got some inertia, it's already got some movement downward, and then once that low-level mesocyclone intensifies, the wind can have a tendency to cut across isobars. We call that cross isobaric flow, and when that drier air from the descending region on the backside cuts into that mesocyclone, you can get what visually manifests as a clear slot cutting into that mesocyclone, appearing to almost cut it into two when that clear slot is substantial enough. On the south side, you get an anticyclonic vortmax developing. On the north side, you get a cyclonic vortmax. And this one on the north side has a greater likelihood of getting coupled with that mesocyclone above, which is behaving like a vacuum cleaner with dramatic vertical motion inside. And once that cyclonic shear on the north side of that clear slot gets coupled with that mesocyclone, it is a candidate to develop into a potentially violent tornado. But if this clear slot is too intense, sometimes a tornado can form, and then the rest of this mesocyclone, there's just not enough mass in there to survive, whether there's a capping inversion, maybe some warmer temperatures just above the ground, and sometimes this clear slot that produces a tornado can be so intense that it actually leads to the demise of the parent supercell. I've seen this happen a lot, especially near sunset, where a supercell looks like it's weakening, and then suddenly it produces a tornado, and then the supercell evaporates into thin air, and that's because this clear slot is just too substantial, punching into the mesocyclone, takes out too much mass of the mesocyclone, and acts to weaken the storm, and you get a beautiful tornado that spins down basically as the skeleton of the original supercell. So that's really the basics of a clear slot, and sometimes if the supercell can survive that occlusion process, then another low pressure develops off to the east. The mesocyclone will regain its relatively symmetric appearance. Another clear slot will punch in, and then you'll get a new tornado, and that's what's called a cyclic tornado producer. The RFD marches forward. You get a new zone where the occlusion process begins, and you don't have total occlusion until the dry air wraps all the way around that vortex, and at that moment, that's when that's likely becoming a tornado or already a tornado, and condensation isn't always a luxury that's available to us to see what's happening inside the storm. But really, that's what's going on in almost every tornadic supercell. A lot of times this process is concealed by rain. Sometimes it's a low precipitation supercell. But let's go back now to the Manitoba supercell and try to break down exactly what happened. When we looked at it that morning in a larger scale, it didn't look like there was going to be a big outbreak of violent tornadoes, but it really only takes ingredients coming together in a small area to get a tornado like what was observed up there in Manitoba. So the image at the left is a radar loop. This is from Radar Omega. The image at the right is a still image, and I can identify some of the features that happened on this day. There was a rapidly lifting warm front the morning of the storm, and you can see in the loop that this is the warm front that's lifting off to the north. There were some attempts at convection to develop along that warm front, but those storms were moving off to the east-northeast, which tells me that they weren't surface-based. They were elevated just north of that lifting warm front. That lifted rapidly up through the region the late morning, afternoon hours. You could also see these moist convective rolls in the open warm sector, showing that at this time, instability was still building. There was still a little bit of convective inhibition, at least off to the east of the warm sector, but you could definitely see there was an instability axis cruising up off to the north here. And initially I thought this feature might have been some kind of a boundary based on radar, but in hindsight, that's just a hail spike or some type of a false radar artifact, maybe generated by that storm along the spoke of that radar beam. But this is actually the tornado producer that was beginning to initiate on a front. You could see a Pacific front back behind. See these horizontal convective rolls within that stable air that are parallel to the westerlies back behind that front. And then it looks like there was some type of a dry line feature or prefrontal trough out ahead of that front as well. And I'm going to show you that on the surface map. So that allowed this storm to develop ahead of the surging cold front, stay ahead of that cold air, which could have acted to undercut it a little bit. And then it seemed to produce the tornado just as the cold front caught up to that dry line. It accelerated the storm motion off to the southeast. There was some cell mergers that happened as well that accelerated that propagation off to the southeast as well. And with some southerly low-level winds at about 15 knots, when you have a 20-knot south-southeasterly storm motion, that gives you a storm relative low-level jet of about 30 knots. And I'm going to show you how that happened on the hodograph and how this storm developed tornado potential. But normally if you're out here targeting, you'd want to target this warm front, thinking that maybe the open warm sector didn't have quite enough ambient storm relative wind shear to produce violent tornadoes. But the warm front or those backed easterlies seemed to have larger scale low-level wind shear to produce a potential violent tornado. But this front was lifting so rapidly to the north that it was never in one location at any given time to allow a storm greater residence time to move along it. But in the end, the open warm sector, that was the target. You had a bulging Pacific front. You had a nose of instability up into this area. You had an area of weaker or due southerly surface winds. You had dew points near 70 or to the low 70s in this environment. and with a south-southeasterly mover, which in southwestern Manitoba, these south-southeasterly movers are notorious for producing incredibly photogenic big-time tornadoes, like the June 23rd, 2007 tornado in Pipestone, like earlier this year in southern Saskatchewan, the south-southeasterly mover, that was a pretty strong photogenic tornado as well. The Tilston one is an exception. That storm was moving off to the north-northeast, that big Tilston tornado. But there you can see that south-southeasterly mover that was accelerated by a couple of cell mergers. And I believe that the cold front caught up to the dry line or the prefrontal trough right as that supercell was reaching maturity. So there you can see that cold front right behind it in the loop. And then bam, it hit it, forced the south-southeasterly storm motion, which really enhanced the storm relative wind shear in the hodograph, enhanced the storm relative low-level jet as well. And you also had a big jet max that was coming in on the south side of that system aloft. So you had 30 to 40 knots, and this storm fired right on the nose of that stronger flow. So there was a very narrow corridor, a narrow space and time window for this storm to produce violent tornadoes, but it certainly capitalized on it. Now I'm going to show you a surface map at the time, around the time of that tornado. I was saving some imagery as this event was happening just because I knew this is an event that we would want to do a recap on. And based on this surface map, you can see that the tornado happened in a relative hole there of surface obs, but you can still get an idea of what was happening. This is up near that retreating warm front that we saw on radar. This environment up here was primed for tornadoes too, but surface-based supercells just failed to develop along that retreating warm front. That left behind an air mass in the open warm sector characterized by south-southeasterly winds at about 5 to 10 knots. Extreme instability though, 77 over 70 type profiles. And this warm front lifted rapidly north, and then you've got a bulging Pacific front, winds gusting out of the west on the backside of that Pacific front, likely a prefrontal trough as well, / pseudo dry line, and that front was surging through western North Dakota as well. Some severe storms also tried to get going further south of the favorable shear down near the Bismarck area. But I always tell people you want to play the nose of the wind shear or the nose of the instability, and that nose was up here into southwestern Manitoba with moisture getting pumped south-southeast to north-northwest. You had a dynamic system up to the north. I'm going to show you that the kinematics, at least in the upper levels, seem to favor a little bit further north to the west of Lakes Winnipeg and Manitoba. But the tornadic storm ended up happening to the south of that prime zone. Here was the RAP analyzed instability around the time of the tornado too. This showing that nose of the instability really well. And of course, I think that the storm relative helicity was way underdone by the RAP in this environment. But you could see a front surging here near the Saskatchewan-Manitoba border. This is our storm that became the tornado producer that's initiating there. You can see quite a bit of SIN, convective inhibition in blue here off to the south of the storm. A little bit of a blob here, though, of no convective inhibition, and plenty of surface-based instability at the nose of that instability axis. You can also see on this RAP analysis, which is remarkable, that it even picked out the hint of the prefrontal trough / dry line with even some west-southwesterly wind barbs in there just ahead of it. But this shows that supercell was able to form in the prefrontal trough out ahead of the actual cold air that would have acted to undercut it. And that actual cold front eventually caught up with that prefrontal trough / dry line once the storm moved a little bit further east, encouraging a rapid dive off to the southeast at about 30 knots as it was merging with some other updrafts. And that really ramped up the storm relative low-level jet as that storm turned into these 10-knot south-southeasterly surface winds. It's also likely that this storm moved in to this area of subtle convective inhibition. That can act to decouple the lower levels of the atmosphere. That can act to enhance the low-level wind shear. That's why you often see tornadoes right at evening during the magic hour, as we call it. As the surface temperatures cool just a little bit, surface winds will weaken or back a bit, whereas the flow just above the ground even accelerates, a bit of an inertial oscillation. And this storm enhanced all of those effects by turning into the right, by propagating south-southeast at a pretty rapid rate into these south-southeasterly winds at 10 knots. So if you have a storm motion that's moving 20 knots to the south-southeast into these 10-knot south-southeasterly surface winds, that's basically a 30-knot storm relative southerly low-level jet that you're dealing with. And when Sean was looking off to the east at that storm, you could almost see what was left of that flanking line feeding from south to north to the east of that tornado cyclone or occluded mesocyclone in there. So really the only target you had was right here, right at the nose of that instability, where it was the only area where there was a lack of convective inhibition. Interestingly, due to a lack of surface obs, the storm relative helicity map here did not capture it incredibly well. But it actually shows pretty weak storm relative helicity available to this storm. But you can see some greater wind shear out here out ahead of it on the order of 150 to 200 meters squared per second squared. You had a bit of a minimum here in the helicity that was behind the dry line, but ahead of the Pacific front that was marching. And this storm actually formed in that well-mixed air between the prefrontal trough and the actual cold front marching there. There was a surface-based instability, a little narrow swath there, likely of some inverted V soundings that allowed that storm to develop, but then it quickly passed into that deeper moisture and enhanced the level wind shear. And look at this, the storm relative helicity here is assuming basically a due west to east storm motion at about 15 knots, but you can definitely see it was right at the nose of a mid-level speed max that was punching in there. That in combination with the cold front merging with that prefrontal trough slash dry line accelerated the storm motion off to the southeast at about 20 to 30 knots at the time of the tornado. The individual occlusion or the tornado is actually moving northeast. So oftentimes you'll see with these strong tornadoes that they will turn left relative to the storm motion, and that's something you want to take into account even if you're observing a tornado from the north side of a south-southeasterly moving supercell. But still, the open warm sector here had some decent wind shear, 150 to 200, and that's assuming a west to east storm motion. And when you superimpose a south-southeasterly storm motion at about 20 knots, enhanced by that propagation into the deeper moisture and the cold front catching up with the prefrontal trough slash dry line, that likely brought that storm relative wind shear a little bit closer to 300. So now I want to look at the upper level map, and this was one that the annotations there were actually from the morning of this event. So I did a severe weather briefing discussing this setup the morning of the event. We talked about two different areas of tornado potential. One up in Canada, right near the Manitoba border, and this was my initial target area that I identified. And then down here on the outflow boundary of that MCV, the MCV ended up moving a little bit further. There were some brief tornadoes that were reported in northern Minnesota there, but that was this subtle disturbance that was out ahead of it. It was an MCV across the upper Midwest. But this is the main vortmax, vertically stacked, almost like an occluding tornado in itself. But look at this flow along the south side of it. A big surge, a big jet streak in the mid-levels coming in here. And interestingly, though, the tornado ended up happening just in the farthest southern flank of that target area. The warm front ended up lifting north a little bit more rapidly as well. And instead of that warm frontal zone being the main target, actually the area in the open warm sector with that south-southeasterly moving supercell on a bulging Pacific front ended up being the better target than the main one that you would identify based on purely upper level kinematics and the nose of this jet max surging on the south side of that feature. But a negatively tilted trough up here as well. There you can see the trough axis negatively tilted, punching through Saskatchewan. Definitely a textbook setup for southeastern Saskatchewan into southwestern Manitoba there. Looking at the 850s, I noticed when I was looking at this in the morning that the main synoptic scale low-level jet was just a bit decoupled from the upper levels. So this is the main synoptic scale low-level jet, and because this upper level system was occluding, it caused this low-level jet to be shunted off to the east. You could see this flow on the backside of that front, a lot of westerly momentum air, even a kilometer above the ground, leading to a bulging type of Pacific front. But you can see the remnants of about a 20 knot low-level jetback here into southwestern Manitoba. And I wonder if that actually verified 25 to 30 knots. It doesn't matter because with a south-southeasterly propagating storm, that 15 to 20 knot 850 wind becomes 30, 35, 40 knots in a storm relative sense up there in southwestern Manitoba. And again, the black annotations there are from the morning of when I was breaking this down. And I did pull up a quick map of energy helicity index the morning of, model derived, and that also helped me to identify these two target areas. One, which was along the outflow boundary in northern Minnesota there, that did produce a couple of brief tornadoes. This is my other target area along the Manitoba-Saskatchewan border, just north of Sean's house, actually. But in the end, this really ended up being the target area, a little bit off to the south, even in that hole of EHIs. And this shows you that the HRRR tends to overmix dew points further north. This was actually a mixing hole to the south of that warm front that had lifted up to the lakes region. And looking at the surface map, dew points verified around 70 to the low 70s there in southwestern Manitoba in that environment where those tornadoes were produced. So you could definitely color this in with a bright red EHI pipe that fed right up into that tornado right there. But that's why using the HRRR could be a flawed approach when you're trying to forecast for the high plains, northern plains, or the Canadian prairies. And usually the RAP model has a tendency to work out a little bit better up there. So let's look at some of these wind fields. At a kilometer up, you could assume a south-southwesterly wind at about 20 knots. Let's look at about 6 kilometers up. You've got a west-southwesterly wind at about 35 to 40 knots. And then we'll use some of the analysis from the surface map and radar to, this is a very messy way of looking at this hodograph, but still a good way to learn hodographs. Here is that blank hodograph page that we were talking about. And similar to that diagram that I just drew for you, this is also looking down at the ground, looking down at the winds. And so we know that the surface winds were south-southeast at about 5 to 10 knots. We'll call it 10, we'll call it 15, we'll call it 7.5 knots at the surface out of the south-southeast right here. So that's your surface wind. You're plotting a vector. It's pointed to the from the south-southeasterly direction up to just shy of 10 knots there. That's your dot for your surface wind. Your dot about a kilometer up was about 10 knots out of the south-southwest. So that's about your 1 kilometer wind. And then your 6 kilometer wind at 500 was close to the due west or west-southwest at about 30 knots. So you had a west-southwesterly wind out there. And your actual storm motion vector was south-southeast, or we'll call it due southeast at about 30 knots, or 20 knots. So this would be your storm motion vector, a combination of propagation, the arrival of that cold front meeting up with the prefrontal trough, surging the storm motion eastward, and an arrival of that jet max that was whipping around the south side of that upper level system, catching up with this storm that became a mature supercell. So really you're looking at a hodograph shape, roughly that looks something like this. And there are probably some other wind barbs in there that will support this shape. But really this hard right mover way to the right of all of these wind barbs, including the upper level winds at about 30 knots, that led to this area contained within the storm motion vector and that hodograph. All of this is available storm relative helicity for this storm. And looking at radar, it was even moving south-southeast at times during that. That brought that critical angle, which is the angle between the storm motion vector and the 1 kilometer shear vector, or 500 meter shear vector, close to 90 degrees, closer to 90 degrees with that hard right turn. And as often happens with these types of situations where you have a very strongly deviant motion off to the right, the individual tornado is actually moving to the northeast. So it's moving well to the left of that storm motion, if not perpendicular to it. once it starts to rope out and gets mature. And that just shows you also how that tornado is completely occluded or cut off from that mesocyclone. But that hodograph looks a lot more favorable than what the RAP was analyzing, assuming those due west to east storm motions, in which case you have a lot less storm relative velocity, which is the area between that storm motion vector and the hodograph curve up there. So you can see that the wind shear was much more favorable for that deviant motion. That goes to show you just how deviant storm motions matter so much for creating a strong, violent tornado like this. And when analyzing the shear, it shows you how sensitive a storm is to the storm motion, rather than just the environmental wind shear or the winds that exist in the ambient environment. How the storm is moving relative to that wind shear is even more important. And so now to close this out, I'm just going to play Sean's video with his audio so you can hear the roar of that tornado. And then I'm going to look on the chat here on the Facebook supporter group and start answering a few of your questions. So thank you everybody for tuning in to my weather reports. There is an enhanced risk today across northern Illinois for the threat of a derecho event. It does look like it's going to be a widespread windbag type of an event. Many straight line wind reports, but that complex of storms is already organizing across portions of the Corn Belt, and that's going to surge across eastern Iowa and northern Illinois later on today. I'll be going live again later on today to break that setup, but really wanted to give this setup a few days ago in Manitoba a deep dive. I'm really passionate about these setups in Saskatchewan and Manitoba. I've seen a lot of big tornadoes up there myself, and this was just an incredible tornado that really showed the storm structure and the internal dynamics that are critical for tornado formation. And also wanted to highlight Sean's work out there in the field and break down the radar loop from Radar Omega, since we just got that Canadian radar data going on the Radar Omega app, which is extremely exciting. So thank you everybody. I hope you learned a lot from this, and I'm going to continue breaking down previous events, continuing to do these case studies, plotting hodographs, breaking down all layers of the atmosphere, and working in a little bit of meteorology. So thank you everybody, and hope you have a great rest of your Monday.
Oh, it's hitting something. Debris. Big tornado. Tornado right above me. Oh, it's hitting something. Debris. Big tornado. Big tornado right above me. Oh, it's hitting something. Debris. Big tornado. Big tornado right above me. Oh, it's hitting something. Debris.